Okay, the purpose of this video is to introduce conceptually the idea of a system property called time-invariance. And the basic idea is that a time-invariant system does not change during or as a function of time. A time-varying system changes. So a time-invariant system, if I put something in and get it out today, and put the same thing in and get it out tomorrow, I'll get the same thing out both times. But with a time-varying system, what the system does to an input today may be completely different than what the system does to an input tomorrow. So I'll try to put this together or make this make sense with two examples, and then in a separate video we'll look at the mathematics behind it. The mathematics are simple, but they're actually quite confusing, so hopefully this graphical illustration of what's going on will make sense and help you when we get to the math. So suppose I have a system. The system has an input. The system has an output. And all the system does is multiplies its input by 2 to get its output. So it's just a constant gain. And we're going to assume that this gain is indeed constant and never changes. Okay, so we're going to do a thought experiment where we're going to put a signal in to the system, and we're going to get the signal out, and then we're going to put the signal into the system after a delay and get the signal out. And we're going to see if the system, if the output to the delayed input is equal to the delayed output of the non-delayed input. That sentence was probably kind of ugly, but it'll hopefully make better sense in just a minute. Okay, so the input that I'm going to use is just an arbitrary thing with a rectangular pulse and then a triangular pulse. This is mostly just to give us something to look at. And if I delay this, it would look like this. And again, the experiment I'm going to run is pass the undelayed x of t through and the delayed version, which I'll call x sub d of t. And this is x of t minus tau. So we're going to delay the input by an amount tau. So the input, when it's delayed, is going to look like this, and this distance is tau. Okay, so let's put these two signals through a system, well, through this system that multiplies everything by 2, and see what we get. So the first signal, everything gets multiplied by 2, so it's going to look something like this. This rectangular pulse is the same duration, but it gets taller in the sense that it has a higher amplitude. The triangular pulse is also the same duration, but it gets taller. Okay, so this is y of t. This is the output due to this input. Now, if I look at what comes out when I delay the input, in this particular case, I'm going to get something that looks like this, where I have my delayed input, which is multiplied by 2, so this is what I am going to call y sub d of t. This is the system response to this input x sub d. Okay, and so the question is y sub d, we'll put this in a different color because this is the question we're asking, is y sub d, this response to the delayed input, the same as the response to a non-delayed input that's been delayed by a value of tau? So if I were to take y sub t, or y of t, basically this guy here, if I delay that by a factor of tau, then it's like shifting to the right by a factor of tau. And it looks like this thing that I've drawn in blue, because this guy shifts over here, this guy shifts over here. And now, if you're willing to ignore the drawing effects, these guys line up. And indeed, this it turns out that this system is time invariant, which is exactly what you would expect, because this system is a constant gain. The gain of this system never changes. So that's an example of a time invariant system. Let's clear this off, and we'll look at another system and see if we can determine whether or not this system is time varying or time invariant. So again, in this system, we still have an input and an output. But now this system is going to be a gain that is the cosine of some omega 0 t. So basically, the gain of this system is going to start at 1, go down, go up, and so on. And we'll assume, for the purposes of this example, so this is a graph of this guy here, we'll assume for the purposes of this example that omega 0, the frequency is very low, so that the output, or this cosine, is changing pretty slowly with respect to the signals that are going into the system. So we're going to do the same thought experiment. We're going to take the same x of t, with our rectangular pulse and our triangular pulse, and see how what the output of the system is then. And we're going to take this delayed version x sub d of t and run it through. Okay, so again, our system is it takes its input and multiplies that input by cosine omega 0 t. So what I'll do is just actually plot this cosine omega 0 t here, and we'll plot it here. And in both of these cases, to get the output, we need to multiply the input by this cosine omega 0 t. So the output in this case is going to look something like this. It's going to be, for the rectangular pulse, I've got something where I've got a constant multiplying a decreasing cosine, so it'll probably look something like that. Over here, in this region, I've got a negative value of the cosine, so my triangular pulse is going to end up being multiplied by negative stuff, so it's going to actually end up flipping upside down. And again, that's more or less accurate. Okay, so over here, when I take my delayed input and run it through, I'm going to get something that looks like this. Oops. We'll do this in green because we want to be consistent. Okay, so here my rectangular pulse is multiplied by a little bit of positive cosine and then a large part of the negative cosine. So it's going to start over here and go down like this. And then my triangular pulse over here is going to start being multiplied by a negative value of a cosine and then end up being multiplied by a positive value of a cosine. So here, we'll get rid of this ugly looking arrow because we're out of space. So this guy is going to have the triangle that starts negative and goes positive. And that's actually probably not the most accurate representation, but hopefully it will do for our purposes. Okay, so now the question is this y of d, the output due to the delayed input, equal to y of t minus tau? Well, okay, so basically the question is, if I shift this y, do I get this y of d? Well, if I shift this y, let's see, we'll draw something like this, because this is what the shifted y looks like. And then I've got something that looks more like this. So again, this part looks like this. The little triangle part looks like this. And you can see, because my artistic abilities are so good, that the shifted output is not, this guy is not at all the same as the input. So this is a time varying, the shifted output is not at all the same as the output in response to the shifted input. So this is an example of a time varying system. And it makes sense because the gain of the system, the thing that I multiply my input by, this changes as a function of time. So the output I'm going to get in response to an input depends on when I put that input into the system. And if I delay the input, then I'm going to get something different. So this is an example of a time varying system. And we'll stop there. Put tomorrow. So I'll try to put this together, or make this make sense, with two examples, and then in a separate video we'll look at the mathematics behind it. The mathematics are simple, but they're actually quite confusing. So hopefully the varying system changes. So a time-invariant system, if I put something in and get it out today, and put the same thing in and get it out tomorrow, I'll get the same thing out both times. But with a time-varying system, what the system does to an input today may be completely different than what the system does to an output. And all the system does is multiplies its input by 2 to get its output. So it's just a constant gain. And we're going to assume that this gain is indeed constant and never changes. Okay, so we're going to do a thought experiment where we're going to put... Okay, the purpose of this video is to introduce conceptually the idea of a system property called time-invariance. And the basic idea is that a time-invariant system does not change during or as a function of time. This graphical illustration of what's going on will make sense and help you with when we get to the math. So suppose I have a system. The system has an input. The system has an